Welcome. We are the Team 19. I am Francesco Vergona, and we can't wait to show you what we have done in the last few weeks. First, a brief history. When Professor Gobbaro came out with the latest hard distances and we tried to solve them with the algorithm we had developed so far, the result we achieved was something like this. Well, we were devastated, but on the other hand, Professor Gobbaro also said if you're able to reach the optimal solution for the S distances, you will be immediately awarded with a graduation. It was in that moment that we all looked into each other's eyes and said, challenge accepted. But now, back to business. Let's start with a short abstract of what we're going to show you today. We're going to analyze in depth the three main aspects which allowed us to reach a quite satisfying solution. First, the change-making problem we use for both the soft and the hard distances. And I have to say that with the change-making problem, we were able to get an always feasible solution. Second, the grasp we use to improve the soft distances. And third, the variable neighbor search we use to improve the soft distances. And now, to take a closer look to the change-making problem, please welcome my associate, Mattia De Prisco.
Hello, everyone. What's the basic idea behind the change-making problem? Let's suppose we enter a shop and buy something for €4, paying with a €10 bill. Now the shopkeeper owes us a change of €6. He has only available €5 bills and €2 and €1 coins. Now, what we are trying to achieve here is to receive that change of €6 using the least amount of coins and banknotes from the one he has available. So, in this case, we should receive a €5 bill and a €1 coin. But what if the shopkeeper has available only less valuable coins? Well, in a real case scenario, it would be something like this. Back to business. What's in common with our assignment? First of all, in the change-making problem, we have a precise set of coins and banknotes that we can choose from. Second, there is a precise change to reach. In our assignment, in fact, there is a precise number of tasks each user can perform and a certain number of tasks to be done in each cell. But we could not just use the change-making algorithm as it was. In fact, there are also some important differences. First of all, we have a limited number of available users, while in the change-making problem, we were only limited by the types of available banknotes and bills and coins, not their number. Furthermore, in our case, overbooking may occur, meaning that 10 users may perform more tasks than needed. But what is overbooking? Let's look at an example. Let's suppose we assign one user which can perform 3 tasks to a cell where there are 2 tasks to do. The overbooking is calculated by subtracting the tasks to be done from the multiplication of the assigned users and the tasks their user type can perform. So in this example, we have an overbooking of 1. Those are some of the variables used in our code, but the most important one are the arrays C of I and S of I. C of I contains the minimum number of users required in order to solve I tasks, while S of I contains the last user type picked in order to solve I tasks. This is our pseudocode, which may look kinda confusing. So, in order to have a clearer look, let's look at an example. The basic idea is that, in order to solve X tasks, we start solving from 0 to X tasks. And in every case, we want to obtain the minimum amount of users and the minimum overbooking. So, in this case, we have 11 tasks to solve, and our user types can perform 3, 6, and 10 tasks. Obviously, in order to solve 0 tasks, we need 0 users. For instance, we take them of type 0. The best we can do in order to solve 1 task is picking 1 user of type 0, same for 2 and 3 tasks, while in order to solve 4 tasks, we need 1 user of type 1, and so on. Once both arrays are filled, we just look at the array S of I to find our optimal combination. Starting from 11, we pick 1 type 0 users, which can perform 3 tasks, leaving us with 8 remaining tasks. Then we pick another type 0 users, leaving us with 5 undone tasks, and then finally a type 1 user. So the optimal combination in order to solve 11 tasks is sending 2 type 0 users and 1 type 1 user. This algorithm performed brilliantly, especially on the S instances, where the total number of tasks to be performed and the total number of tasks all users could do were really close quantities. But it also helped us improve our solutions in the standard instances. In fact, being able to always send a minimum amount of users considerably cut down the costs. Now, in order to explain in greater detail how this initial combination is taken advantage of in our code, I'll give the floor to my colleague, Nico Caprioli.
Hello, everybody. In this section, I will talk about the metrics we use to solve both soft and hard distances, which are the grasp and the VNS. First of all, I will talk about the grasp. The grasp is a metric for combinatorial problem which has two phases. First, an iterative construction of grid randomized solution, and then an improvement through a local search. If you take a look to the pseudocode, it may be quite confusing, so I will explain it in details in this slide. Given a random destination cell and the amount and the type of the user required, which are computed by the change-making problem, it looks for the minimum pair, starting cell and time slot. I have to say that this is the only method that sometimes runs in a multi-thread environment. We use the grasp when other meta-heuristic runs out of user too quickly, which means that it's useful to improve our distances such as the ST instances, while it's less suitable for the standard distances. Now the grasp is more clear, I will talk about the variable neighbor search. Before the VNS, as Professor Gobado pointed out, we had a problem in selecting the proper size for the neighborhood. So we came out with an idea. We're not using a meta-heuristic which automatically chooses multiple sizes for the neighborhood. Well, that's exactly what VNS does. So we may look now how we generate a neighborhood. At first, we drop a set of random destinations, random tuples from the solution table, and then we recompute the minimum for each deleted tuple. So, as I already mentioned, the VNS computes drops the tuples run choosing the size of the neighborhood. So given an initial percentage K0 of tuples to be dropped and a maximum percentage K0 of tuples to be dropped, it dynamically changes the percentage of dropped tuples from K0 to Kmax. If we take a look to the pseudocode, we can see that we start from K equal to K0, which is the variable that says how many tuples we will drop. Then, if we find a new improving solution, we reset it to K0. Otherwise, we increment it by 1%. The advantages of VNS is that it improves the fitness for standard distances, and it's very fast as it retards a stable solution in around 2 seconds. This is true, of course, for bigger instances, while for the smaller one, it converges in around 180 milliseconds. So, as it is so fast, we can think to rerun it from the beginning in the remaining time, so because it is random, and so it can only improve the fitness. Now, for a brief summary and results, I will give the word back to my fellow Francesco Vergona.
Hi again. Let's take now a look to the results. First, before showing the results, I want to say that we obtained these results by using a single-threaded environment. In fact, there's only one method which runs in a multi-threaded environment. We decided to split the results into two parts. First, the soft distances, and second, for the hard distances. For the soft distances, here you are the minimum, the average, and the maximum optimality gap we were able to achieve. As you can see, we are very far from the 2% threshold. That was the assignment objective. And now some extra statistics. We had 120 different soft distances, and on 24 cases, we came out with a 0% of optimality gap. That means almost the 20% of times. And then we were also able to get a global average optimality gap of 0.21%. And now, the hard distances. Before showing the results, I have to say that with our algorithm, we were able to solve both the 100 and the 300 distances with 20 times lots. But there were no optimal solution provided, so we didn't plot them on the slides. And now the hard distances, here you are with the minimum, the average, and the maximum optimality gap we were able to achieve. As you may notice, we were not able to stay below the 2% threshold for each hard distance, so we're not going to get our graduation today. If you got any question, please ask, but if you don't have any, we're both scared and happy.
Okay, we have a problem, of course, because you have a blue shirt and that's a very big problem because your section was red.
I have two sections, one green and one red. I can't be. I have
the
to
problem
stay
is the
here with
same.
the.
You don't have a green.
I
and
have to
red
be with
shirt.
the Italian flag. White, red, green,
Yeah,
red.
yeah. Probably you have. Okay. So we have a problem. You have a very big penalty for that, and yeah, no, probably -20. Okay, so great presentation, interesting and funny. I don't have any question.
The languages, the language that you use.
Yes, C#.
Okay, C#.
What about the threads? Threads.
It runs in a multi-thread only in VNS for finding the minimum. So well, it scans the matrix of the cost to find the minimum pair. It works both on a single thread and multi-thread. Actually, there is no such big difference. In fact, on small instances, it's actually better in single thread because the overhead to span a thread is more than the thread that we look on the instances.
Okay. So your algorithm runs just for 2 seconds, not for all the time.
5 seconds.
Okay.
Once it goes to Kmax,
okay,
it
then you
restarts from
restart
scratch.
Okay. Do you have any idea to improve your algorithm?
Maybe.
Just one?
I don't know. Maybe if we add new random, which can explore more solutions.
Okay. Thank you very much.